Welcome back. We're now on 8.4, Molecular Orbital Theory. This is the longest section in the book and probably the most confusing. So take your time going through this. In this section, we're going to outline the basic quantum mechanical approach to deriving molecular orbitals from atomic orbitals, describe traits of bonding and anti-bonding molecular orbitals, calculate bond orders based on molecular electron configurations, write molecular electron configurations for first and second row diatomic molecules, and relate these electron configurations to the molecule stabilities and magnetic properties. So we're first going to talk about the thing I alluded to at the very beginning of chapter 8. Why is oxygen gas attracted to magnetic fields? So if you have a molecule with unpaired electrons in it, it exhibits what is called paramagnetism. And these are attracted to a magnetic field. They appear heavier in a magnetic field due to the force that's being exerted on them, which can be used to calculate unpaired electrons. So oxygen, which here's the structure of oxygen gas, in the Lewis structure, does not appear to have unpaired electrons. Everything was paired up, yet it displays paramagnetism. So this was a mystery to scientists. Why is this happening? Whereas it was more expected to be diamagnetic, something like nitrogen gas is diamagnetic, meaning all the electrons are paired and it actually weakly repels a magnetic field. And if you put it in a magnetic field, its apparent weight actually decreases. So this is where molecular orbital theory, or MO theory, comes into play. It explains paramagnetism, octet rule violations, and other complicated bonding schemes, many of which we're not getting into here. So it's going to combine atomic orbitals to yield molecular orbitals that are delocalized over the entire molecule rather than be localized on its constituent atoms. So now we're going to expand on what we did in the last section. All of this comes together with molecular orbital theory. And this is just showing a GUI balance, compares the mass of a sample in the presence of a magnetic field compared to the mass without the magnetic field to determine the number of unpaired electrons in a sample. So notice how if it gets heavier, so if this goes down, then you know that it's paramagnetic. So let's talk about molecular orbital theory. It describes the distribution of electrons in molecules. Think Lewis structure, now think bigger. So also similar to the electron distribution in atomic orbitals, it is described by the wave function. Okay, so the region of space in which a valence electron in a molecule is likely to be found is called a molecular orbital. So now, instead of talking about atomic orbitals, we are talking molecular orbitals. Okay, and they're abbreviated with the psi squared symbol. Couple terms. Homonuclear diatomic molecules have two identical atoms, something like O2, N2, F2. These are homonuclear diatomic molecules. We have a mathematical process of combining these orbitals to generate molecular orbitals. It is called linear combination of atomic orbitals, or LCAO. And this is, for those of you that are interested in this kind of stuff, this is something you could do in graduate school. You do molecular modeling work. Not something that is my cup of tea, but some people really enjoy it. So what happens is it looks at how the wave functions combine. If they have constructive interference, so like we talked about in chapter 6, where the peaks are going to line up, you have what is called an in-phase overlap. And then when you have destructive interference, when the peaks and troughs line up, you have out-of-phase overlaps. So these overlaps give us two different types of orbitals. The in-phase overlap gives us a lower energy molecular orbital, sigma s. Okay, so now instead of just saying a sigma bond, we have a sigma s molecular orbital. So this has the most electron density between the nuclei. The electrons are attracted to both nuclei at the same time. So this is the force that's holding them together. And these are called a bonding orbital. So this is where you're making that nice bond. The out-of-phase overlap leads to a higher energy molecular orbital called sigma S star. So that doesn't mean it's the star. The electrons are located away from the region between the nuclei, and the attractive force between the nuclei and the electrons pulls the nuclei apart. So this is an anti-bonding orbital. So just to kind of show you what we're talking about with our waves with the constructive and the destructive interference. So if we have these two s orbitals combining, these two atomic orbitals, they can either add together to form the sigma s bonding orbitals, or they subtract to form anti-bonding sigma s star orbitals. And these are, again, molecular orbitals. These are not atomic orbitals. Now, when p orbitals overlap, the wave functions result in two lobes with opposite phases. So same like the sigma star and sigma s. When the same phases overlap, constructive interference gives us that increase in electron density. The opposite phases give us the destructive interference, decreasing our electron density and producing nodes. When we have the end-to-end overlap of p orbitals, we get a sigma s and a sigma s star. When you have the side-by-side p orbital overlap, you get a pi bonding molecular orbital and a pi star anti-bonding molecular orbital, similar to the sigma s and sigma s star orbitals. So valence bond theory tells us that pi bonds have a nodal plane in the internuclear axis, and it's perpendicular to the p orbital lobes with electron density on either side of the node. It's the same shape in molecular orbital theory. And the electrons can interact with both nuclei to help hold the atoms together. The out-of-phase pi star antibonding molecular orbital gives us two nodal planes, one along the internuclear axis and one perpendicular between the nuclei. So this is what the sigma p and sigma p star orbital look like. Okay, so we looked at the sigma s and sigma s star. So now here's sigma p and sigma p star. I mean, these are showing the ones along the x-axis, but it doesn't really matter. They're all going to be the same shape. When you have that side-by-side overlap giving us the pi p and pi star p orbitals, you can see the bonding orbital on the bottom versus the anti-bonding on top, and you see the two nodes for the anti-bonding orbitals. So each atom has two sets of side-by-side p orbitals in the molecular orbitals of diatomic molecules. So when you have four orbitals, these are going to combine to form two pi orbitals and two pi star orbitals. So you get like a pi py and a pi pz orbital, and these are degenerate. So remember, degenerate orbitals are identical in the same energy except orientation. And the pi star py and pi star pz antibonding orbitals, but again are degenerate and identical except for their orientation. If you have 6 p orbitals in two atoms, you get 6 molecular orbitals. So notice the number of molecular orbitals, same as the number of atomic orbitals. So just to kind of go through the 6 total, and I stress the total because we're just looking at 2 sets of p orbitals. Okay, we have 4 orbitals making 4 orbitals, and that was from the p, but 6 total. So now we're including the pi or the sigma orbitals. Okay, we now from the 6 atomic p orbitals in 2 atoms, we have a sigma px, sigma star px, pi py, pi pz, pi star py, and pi star pz. So let's look at an example where we want to predict what type, if any, molecular orbital would result from adding the wave function so that each pair of the orbitals shown overlap. And we're told that they're all similar in energy. So this first one in A, this is in phase. We see the side to side. So that side to side tells us it's going to be a sigma. And since they are in phase, they're the same color. That means in the 3p, it's going to be a sigma 3p orbital. In B, we see these guys are not orientated properly, so these will not form an orbital because they can't overlap like they need to. In C, we see the side-to-side orientation. So there could be some orbital, but this is an out-of-phase combination. They're opposite colors. So that means this is going to be a star. Since it's side by side, it is a pi, and then it's 3p, so it's pi star 3p. Here's another example. We want to figure out if this is sigma or pi, bonding or anti-bonding, and tell where the node occurs. So when we look at this, we see it looks like it's side by side. Okay, so side by side means it's sigma. But they are out of phase, blue and red, so that means it has to be a sigma star. And because of that, we're going to have a node right down the center. So this is an anti-bonding molecular orbital. This is just a salute to Walter Kohn, who developed some of the methods to describe molecular orbitals. Look at that hat. Molecular orbital theory and computational chemistry are very important for pharmaceutical research, actually. So a lot of biochemists that are interested in computational chemistry do this type of work. I actually had a few friends in grad school for chemical engineering who were doing this type of thing as well. So they can use molecular orbital theory to try to design molecules to bind to the, for instance, HIV protein and try to inhibit the progress of the disease. So very important and pretty amazing work that I very much appreciate. I just never was able to understand it, to be quite honest. So let's talk about molecular orbital energy diagrams. So these show the relative energy levels of atomic and molecular orbitals. Two atom molecules show the atomic orbital of one atom on the right and the other on the left. And you put a horizontal line to represent one orbital that could hold 2 electrons, just like we've done before. And the molecular orbitals are formed by the combination of atomic orbitals, and you put them in the center. You use dashed lines to show which of the orbitals are combining to form the molecular orbitals. So you always have one lower energy bonding orbital and then a higher energy anti-bonding orbital per pair of atomic orbitals. Then you fill in that diagram the same way you did with atomic orbitals using the Aufbau principle. Lower energy orbitals are going to fill first, 1 electron per degenerate orbital. So just like we've done in the past. We also have molecular electron configuration, and we do it with the orbitals, with superscripts indicating the number of electrons in the orbitals. A lot of times the core electrons are emitted, and only the valence electrons are used. We use parentheses around the molecular orbitals that have the same energy to show that they're separate. So for instance, Be2 plus has 7 electron. It's a 7 electron molecule. So doing its molecular electronic configuration, we have sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s1. And this is the molecular orbital for just the valence electrons of that Be2 plus. Notice we had a full 1s shell, so we're just looking at this 2s. So we take the electrons, one of the berylliums has 2 electrons, the other has 1 electron. Okay, and so then we have 2 orbitals. We're forming 2 molecular orbitals, a sigma 2s and a sigma star 2s. So we have these 3 electrons now. We're first going to fill in the sigma 2s and then go up to sigma star 2s. Another thing we can use to identify the strength of a bond and if a bond is actually going to occur is using bond order. And so this results We can do this after you fill the molecular orbital. You take the number of bonding electrons, subtract the number of anti-bonding electrons, and divide it by 2. The higher the bond order, the stronger the bond. If you get a bond order of 0, then you have no bond formed. So, for instance, hydrogen, H2 molecules, are readily forming because the energy of the molecule is lower than that of the 2 hydrogen atoms. You have a sigma 1s orbital that's lower than both the 1s atomic orbitals from the hydrogens. And it gets a bond order of 1. So you have 2 bonding electrons minus 0 antibonding divided by 2 gives us a bond order of 1, a single bond. He2, or dihelium, will not form because the stabilizing effect of the 2 electrons in that sigma bonding orbital get offset by the sigma star orbital destabilizing it. And we have a bond order of 0. 2 bonding minus 2 antibonding divided by 2 is 0. So this is the molecular orbital diagram for hydrogen, for H2. So each hydrogen has 1 electron in the 1s orbital. And so we make our molecular orbital diagram that results, and we get 2 electrons in the sigma 1s, no electrons in the antibonding orbital. So this forms and it's stable. And this is the molecular orbital diagram for dihelium, He2. And you can see we have 2 electrons from each helium. We first fill up that sigma 1s, but then we still have 2 electrons, and we fill up the sigma star 1s, and we see then that then destabilizes it, bond order of 0, diatomic helium does not occur. So let's talk a little bit about the second period elements. So period 2 on the periodic table, and their possibility of forming diatomic molecules. So we're talking about the possibility of forming Li2, Be2, B2, C2, N2, O2, F2, and Ne2. Okay, so just went straight across the periodic table. So valence electrons are assigned to valence molecular orbitals with the lowest possible energies, just straight up Hund's rule, like we've done. While sigma bonds are generally more stable than pi bonds, it's actually not always the case, and this comes into play in the second period atoms, and we'll look at what this looks like in the next slide. The atoms that have 3 or fewer electrons in the p orbitals have a sigma p orbital that's actually higher in energy than the pi p molecular orbitals. So this causes an orbital ordering switch, and this is due to sp mixing. So this influences the energies of existing molecular orbitals and occurs when an s and p orbital actually have similar energies. So the sigma s and sigma p wave functions end up mathematically combining, and what happens when this occurs is the sigma s orbital becomes even more stable, but the sigma p orbital becomes less stable and higher in energy. And the same thing happens with the antibonding orbitals. So lithium, beryllium, boron, carbon, and nitrogen all have sp mixing because the 2s and the 2p orbitals are somewhat similar in energy. However, oxygen, fluorine, and neon have a larger energy difference between 2s and 2p, so the mixing is negligible and it goes back to the original order that we would think would happen with our bond orders. So this is the molecular orbital diagram for these diatomic molecules in the second period. So you see them all up on the top. And you can see the sigma 2px orbital, how high in energy, it is. For our first 5, it's higher in energy than this pi 2py and 2pz orbitals. But once we hit oxygen, then it goes back to where it should be, being lower in energy. And that's again due to the sp mixing. But you now have these nice molecular orbitals that you can use. For instance, if you're doing practice problems on your homework, you have them for these diatomic second period atoms. And then this is just, again, showing the sp mixing. So let's look at the oxygen molecule again. Let's go back to that guy and use its the molecular orbital theory diagram. And we end up having one electron in the pi star 2py and one in the pi star 2pz levels. These are now unpaired electrons, and why oxygen is paramagnetic. Here is its molecular orbital diagram. So we have two oxygens, and looking at their valence electrons, we have 2 electrons in the 2s and then 5 in the 2p orbitals, atomic orbitals. And then we combine to make our hybrids, our molecular orbitals. We start by filling up the sigma 2s. So we have a total of 10 electrons. So 1, 2, and then we go up to sigma star, 3, 4, sigma px, 5, 6. Then the pi, 2py, 2pz. Remember, we do one at a time, 7, 8. I'm sorry, this is 12 electrons. 9, 10. And then we have 2 electrons left over that go into the pi star orbital up here, the pi star 2p orbitals. And now we see the unpaired electrons explaining the paramagnetic properties of oxygen gas. Interestingly enough, you can do the same type of thing for like the lithium Li2 atoms, even though we say this is for really covalent. Li2 is actually a possible combination and somewhat stable. If you were to have some lithium vapor near its boiling point, there actually is this dilithium present. Kind of cool. So let's look at example 8.6, molecular orbital diagrams, bond order, and number of unpaired electrons. So it wanted us to do the molecular orbital diagram for oxygen, O2, and then calculate the bond order for oxygen. How does this account for the paramagnetism of O2? So we've looked at the molecular orbital diagram already. And to figure out the bond order, we need to take the number of bonding electrons. So looking at this, we have 2, 4, 6, 8 bonding electrons. And our anti-bonding electrons, so these are the anti-bonding orbitals, 2, 3, 4, divided by 2, that gives us 4 over 2, gives us a bond order of 2. Hey, look, oxygen has a double bond order of 2. And this is greater than 0. This is a stable molecule. And the paramagnetism is explained by the 2 unpaired electrons in that pi star 2p orbital. So here's another one. We want to give the molecular orbital configuration for the valence electrons in C2 2-. Will it be stable? So I copied and pasted the orbital diagram looking at our atoms, and we're going to just kind of isolate C2 here. So carbon has 4 valence electrons times 2 is 8, plus we have 2 extra from this -2. So we have 10 electrons. So let's fill this in. We're going to start with our sigma 2s. So that's 1, 2, 3, 4. It's sigma star 2s. We're now going to move up to pi 2py 2pz. 5, 6, 7, 8. And then our next orbital is the sigma 2px. 9, 10. So we can go ahead now and do the valence electron configuration. Just why not? So we are starting with, I'm going to do it here at the top. We have a sigma 2s, and there's 2 electrons. Sigma star 2s has 2 electrons. And just for order's sake, we're going to do the sigma 2px next. Oh, no, we're not. Just kidding. Never mind, we're gonna go just in energy order. Okay, so now we have pi 2py, and then we're gonna do comma pi 2px 4, and lastly sigma 2px 2. So it looks like it should be stable, but let's go ahead and calculate the bond order just to be safe. The bond order, we have 2, 4, 6, 8 bonding electrons minus 2 anti-bonding divided by 2, 6 over 2. We have a bonding order of 3. So this should be a stable molecule. And apparently Dexter wants to say hi to you guys. He has a lot to say about molecular orbital theory, I believe. Thank you for your knowledge, Dexter. I hope you all feel enlightened by Dexter. And I believe that brings us to the end of chapter 8. This is just another little thing to show you with molecular orbital theory. It's actually used to explain semiconductors. So in solids, molecular orbitals are described actually as band because they're closely spaced together. It's lower in energy, and the conduction band is higher than energy. The valence band and the conduction band have a pretty big difference in energy. The size of the band gap is really what determines the type of solid between the valence and the conduction bands. The smaller the band gap, the better the conductor that this metal can be. So a conductor generally has a small band gap, so like our metals. Insulators have a large band gap so that the electrons have a hard time moving between the valence and conduction bands. So conductor, the electrons can move pretty easily in between. Semiconductors, so like things in electronics, have a kind of in-between band gap. So the electrons can move, but not as easily as a conductor, but it's not as difficult as an insulator. So these are our metalloids. They tend to be semiconductors. So with Dexter's knowledge and that, we have finished chapter 8. I'm giving you guys 2 weeks to go through these lectures. So I'm just uploading them all into week 11. And then you have week 11 and 12. Week 12 is when I'll put the assignments up. Okay, guys, hope you're staying safe. And if you have any questions, as always, know you can reach me.